Hello, my name is Marcus Prier and I'm a physicist at the Forschungscampus STIMULATE at the Otto von Guericke University, Magdeburg in Germany. Today I want to show you our open source console for real-time acquisition, short OCRA, Tabletop MRI System. The tabletop is built in cooperation with the Martinus Center in Boston, which belongs to the Harvard Medical School and the MIT. At a science day at the Martinus Center for my main project, I met the original tabletop MRI system built by the group of Larry Wald for educational purposes at the MIT. You can see it on the right hand side. It's basically a wooden box with brass foil for RF protection, and inside is the magnet. I also met Thomas Witzel with his open source console for real-time acquisition, short OCRA project, where he programmed a software for a small commercially available FPGA microcontroller, the Red Pitaya. With the cooperation agreement, we were able to send students to the Martinus Center. This was my second science day where I developed the OCRA1 gradient waveform generator board. In the middle you see Thomas Witzel, and on the right hand side two of my former students, Ivan Fomin, who developed the gradient amplifier for us, and David Schote, who programmed the first graphical user interface for the OCRA. Since 2019, we also use the tabletop for educational purposes. Every year we have the course MR System Engineering, where students can build hardware and software for the tabletop in our laboratory. This is our latest state for our OCRA Tabletop MRI System. On the left hand side you see the big magnet box with a permanent magnet and where the chemical test tube sample gets put in. On the right hand side you see the OCRA console and below the gradient amplifier. For the magnet we developed two versions in the meantime. We started with the big magnet with 0.4 Tesla field strength in a 50 mm measurement volume. On assembly this was very hard due to the enormous forces of the magnets. We figure out that the alignment and field homogeneity is much more important than field strength. So we go a step back to smaller magnets, which we can align much better. With this we achieve a field strength of 0.26 Tesla. Here you can see our small magnet, which contains of two permanent neodymium magnet discs at top and bottom. Around is the iron yoke. Inside are iron pole shoes. The groove you see on the iron pole shoe is called pole shoe modulation and was simulated with different diameters and depth to achieve the highest field homogeneity. We simulated a field inhomogeneity of 11 parts per million, and after assembling we reach about 80 parts per million. The magnet contains a 3D printed rack where you can slide in the electronics. Here you can see the planar gradient coils. The RF coil is basically the same design as from the Martinus Center. Just a piece of copper wire as a solenoid coil around the chemical test tube. But instead of copper tape as an RF shield, which is unreliable for tuning, we changed the design to 4 PCBs in a rectangular shape that get soldered on the edges. The designers of the original tabletop gradient coils, Feng Jia and Philipp Amrein of the University Freiburg, simulated a new set of gradient coils for us, which fits our construction. To the original coils for XYZ and the shim Z2, a B0 coil was added. This allows for compensating the temperature-dependent field drift of the permanent magnet. Inside the magnet box there are two additional shielded housings, which contains the RF chain and the gradient filters. The RF chain contains a 1 watt RF amplifier, the transmit-receive switch, and first and second stage low noise preamplifiers for a received spin signal. The gradient filter box contains the connections for all the gradient channels and feed-through capacitors to shield noise from the gradient amplifier. On the back of the magnet box you got two connection panels then. On the left hand side the RF panel for transmit, receive and switching signals, and on the right hand side the gradient channels. The OCRA console fits in a 1-unit 19-inch housing. The console contains two major components: the commercially available microcontroller FPGA RedPie that handles the RF signals. It has two transmit and two receive channels with sampling rate of 125 megasamples a second to allow MR signals up to 40 MHz. It also has GPIO pins where we provide a SPI signal to control external hardware. The external hardware is mostly the OCRA 1 board, which contains four 18-bit low jitter digital to analog converters for the gradient waveform generation, but also an RF attenuator to scale the RedPie output to the RF amplifier input. This is the inside of the console. You can see a big power supply and a power distribution printed circuit board, the RedPie microcontroller and the OCRA board. This is the backside of the console with all the connections. The connections and signals are really general, so you can connect almost any MRI to it. We have transmit pulses, receive signal, we have the TX gate, which switches between transmit and receive mode, and the four gradient channels. The console also provides power for the magnet transmit-receive switch and RF amplifier. Our 4-channel gradient amplifier comes in a 2-unit 19-inch rack housing. It has status LEDs on the front for each channel. Inside there's overcurrent protection to protect the coils and temperature protection to protect the end stage for each channel. This is indicated by the status LEDs. The channels can then be reset via a button. On the inside you can see the big power supplies and the amplifier printed circuit board, but also a fan for cooling. The power supplies have ±15 volts. On the back of the gradient amplifier you see the input and output connections. The input can directly connect it to the OCRA console and handles ±10 volts. This gets amplified to ±10 amperes on the output. The software is split in front end and back end. The front end contains the graphical user interface, which is written in PyQt and Python, and we let it run on a Raspberry Pi. The back end is a server in C code, which runs on the RedPie. This talks to the memory and the FPGA and can send out pulses, receive signals, switch between transmit and receive mode, and talk via SPI bus to external hardware like the OCRA 1, which provides gradients. In between the front end and back end, a simple TCP/IP socket protocol transfers the data. I will now show the graphical user interface. The images were captured at February 2022. The look of the graphical user interface might have changed due to the rapid development of the software. The Relax 2 graphical user interface I programmed in the last month is based on Relax by David Schote. If you execute the main Python script, a dialog will appear where you type in the RedPie IP address and connect to it. Then the main window will appear. Here you can select spectroscopy, projection, imaging, or if you want to measure T1 or T2 times. You can open the parameter window to set all your MR parameters like TE, TI, TR times, pulse lengths and amplitude, but also shim and gradient amplitudes. These parameters are saved globally and are used in every sequence. You can close the window or even the software, because these parameters are saved in a file and will be loaded up the next time you open the window. Here you see a tabletop spin echo spectrum. On the bottom you see the time domain and the sampling window with the sampling time TS. In the center appears the spin echo blob at TE. On the top you see the frequency domain and the resulting peak from the Fourier transformation of the time signal. On the bottom left you see all the calculated values from the peak, like the maximum, the surrounding noise, and the resulting signal-to-noise ratio. When doing projections, a readout gradient along one spatial dimension is applied, like x, y, or z. Here you can see a 3D printed sample with two small holes, where the water is in and where we get the signal out. When the gradient is applied orthogonal to the holes, just one peak appears. This you can see in the X spectrum. When the plane is along the holes, two peaks will appear. This is what you see in the Y spectrum. And when combining X and Y spectrum by just multiplying them, you just get a simple reconstruction which you can see in the image. This slide shows the T1 measurement. On the right-hand side, you see the linearization of the amplitudes over different inversion times and the linear regression to get the T1 time. The same goes for the T2 measurement, where the saturation inversion recovery sequence is used. Here you see a general spin echo image from a star-shaped 3D printed sample. The sample has a diameter of 8.4 millimeters. The image is 256 by 256 pixels. The software offers lots of different imaging sequences, like gradient echo, spin echo, turbo spin echo, radial imaging, or EPI. Here you see slice selective spin echo imaging on a small blood vessel-like sample. It goes from one bigger diameter to two smaller diameters. With this, I want to thank you for your attention. If you have questions about OCRA or Tabletop or its components, contact me via my email address. All open source publications from our project can be found at zoidmetographics.org/OCRA.